Okay, in number 4, we've got this curve right here given to us by f of x is 6 over 1 plus x squared. R is the shaded region between that and y equals 3. So first things first, we're trying to find the area of region R. So that's going to be a definite integral now of our top curve minus our bottom curve. So top curve is going to be that curved function right there, 6 over 1 plus x squared. Gotcha. And then minus the bottom curve, which is y equals 3. We're integrating with respect to x, and for our limits of integration here, we could go, let's take a look here, guys, left and right. We better find out where this point of intersection actually is. It sure looks to me like it's at 1, but I would probably want to verify that real quick just by thinking about what happens when I put a 1 in right here. 1 squared is 1. Plus this one is 2, and 6 divided by 2 is 3. Yeah, that's what's going on. So this is the point 1, 3. That means that this point over here is negative 1, 3. So you certainly could go from negative 1 to 1 for your limits of integration. But since this is one we're going to be doing by hand, I think it would be a lot easier to recognize these are both even functions and just integrate from 0 to 1 and then double that result. So what's that going to do for us? We've got a 2 times, and here we go. Now remember, guys, this is 6 times 1 plus x. Ooh, that's a tough one, to the negative 1 power. We can't, what I was just thinking we could do, we can't just reverse the power rule because the derivative within contains a variable. So now we've got to look at this a different way, and this is kind of sneaky, guys. The 6 is just kind of an afterthought, but if this was a 1 over 1 plus x squared, that would be the derivative of inverse tangent. So this is 6 inverse tangent of x. That's when you kind of had to look at it for a minute and see if you recognized the integrand as a derivative from back in the first semester. Then minus a 3x. That's it for the antiderivative, and we're going from 0 to 1. Okay, what's that going to do for us here, guys? Let me go up here just in case I need the space. That's going to equal 2 times, and let's put a 1 in here. Inverse tangent of 1 is going to be pi over 4, and times 6, that'll end up being a 3 pi over 2. And then minus 3 times 1 is just going to be 3. Now that's what you would get from putting the 1 in there. Let's not make an assumption here. Minus, and when you put 0 in, inverse tangent of 0 is 0. 3 times 0. Okay, so that whole thing just becomes 0 right there, but at least we thought about that. Okay, so now I think I'm going to distribute that 2 in there and end up with a 3 pi minus 6, and I don't think there's anything else we can do to clean up that answer there. That's what we've got for that area of region R. Now just a real quick check, everybody. You want to make sure the area of a region should not ever be negative, and the value of 3 times pi somewhere in the neighborhood of 9. 9 minus 6 is still going to be positive. So that doesn't guarantee I got it right, but a negative answer would have guaranteed that we got it wrong. Let's take a look at B. Write but do not evaluate an integral expression for the volume of the solid generated when R, that region, is rotated about the horizontal line y equals 7. So let me just draw kind of a quick version of this curve here yet again. And we had a curve that went up. It doesn't look exactly like that, but okay. And then here is the line y equals 3, and y equals 7 is this line right over here. So what's happening here, guys? We are now taking this entire region, which is going to be this whole chunk right over here. Actually, I take it back. It's all of that. There you go. And we're going here around or about this horizontal line. That tells me that this is a dx problem. And with all of this gap here between the curve and the axis of revolution, we're going to be doing washers. So the formula for area of a washer is going to be pi times big R squared minus little r squared. Okay, then let's figure out what big R is. And you know what? I think I'm going to need a third color here. Let's switch to green. Big R, I always start drawing from the axis of revolution, and I go through the first curve and down to the second. So that I just drew there is capital R. Now you'll notice here, guys, no matter where it was that I drew that, not you, Jiminy Christmas sticks. All right, no matter, there it is. This value is always going to remain constant here, guys. It's the value of 7 minus 3, so we're going to end up with, let's try to put things back, we're going to end up with 4. as a constant value of big R, 7 minus 3. Little r is more complicated. We start at the axis of revolution again, and we go down until we hit the first curve, and that's little r. So, how do we measure little r? Top function is y equals 7, and then minus the bottom function, which was the 6 over the 1 plus x squared, and that's what we have for little r. So, that would be messy to deal with, but luckily they told us only to write the integral and not to bother evaluating it. So, back to where I was in blue, area as a function of x now is going to be pi times the quantity, big R squared. You can write it as 4 squared, but I'll go ahead and put a 16 right there, and then minus, and little r is 7 minus 6 over 1 plus x squared, quantity squared. So that's pi times big R squared minus little r squared. And now that's the hard part of volume. So volume will now equal the definite integral of whatever your a of x function is. And since that one was kind of a pain in the neck to write out, I would probably be smart just to write a of x right here, taken with respect to x, and let my grader realize that I've already defined what that is right here so that I don't have to write it again. All that's missing are limits of integration, and once again, you could go from -1 to +1, but I think it would be a good idea to double this thing, going from 0 to 1. Although since we're not actually evaluating it, I really couldn't care less if we went from -1 to +1. Okay, so that's what I've got for part B right there. And on to part C, the last part of this problem. And this is one that bothered some people because it felt like something we hadn't talked about before. They're always going to throw you on the AP test at least one new thing that you're going to think you don't know how to do, but I promise we've got the tools in the box here, guys, for how to do this. So let h of x be the vertical distance between the point x, f of x. And let's remember that f of x was that curved function we were dealing with here that looked something like that, and then the horizontal line y equals 3. So h of x is the vertical distance between the two of them. So that little red mark right there represents h of x. All right, and then find the rate of change of h of x with respect to x at x equals 2. Now that location right there made something interesting, and I'll tell you guys where I made a mistake on this question the first time I went through it. Okay, I'm looking for a rate of change of h of x, which tells me that I need a derivative, but before a derivative, I need a function. H of x is the vertical distance between these two curves. So it would be the top function there, which is going to be 6 over a 1 plus x squared minus the bottom function, which is y equals 3. And then I said, okay, h prime of x, here we go. All right, for that one, I probably would write this as 6 times 1 plus x squared to the -1 power. That derivative then would be -6 times 1 plus x squared to the -2nd power times the derivative within, which would be a 2x. Okay, got that, and the derivative of the -3 at the end is just 0. So that function, that derivative, represents the rate of change here, and I suppose I could clean that up a little bit to make that a -12x all over 1 plus x squared, quantity squared. Now, that's what I had here right now, guys. The mistake that I made here had to do with the order of my subtraction. I'm looking at this curve right here, and I was looking in this region here and saying, okay, the top function is the curve, the bottom function is the line, and that's the way we wanted to do it. Except remember, guys, this point of intersection right here was x equals 1. X equals 2 is twice as far to the right. So when we measure the vertical distance between these two curves at the point in question, that means I've got this order of subtraction wrong. That means that what this really should have been was 3 minus 6 over 1 plus x squared. Now the derivative of that 3 is still 0, but there should have been a minus in front of all of this, which means this minus should have canceled out, but my answer then should be the opposite sign of what I had. So really, guys, that numerator should just be positive 12x. x. Okay, so that is the true rate of change here of that distance in the neighborhood then of when x equals 2. So to find that rate of change, we're going to evaluate h prime of 2 and get a 24 on top. And on bottom, 2 squared is going to be 4, plus 1 is 5, and 5 squared is 25. 24 over 25 is the answer that we came up with. When I did this incorrectly the first time through, I had negative 24 over 25. But as soon as I looked at it, I said, oh, okay, as you move here from right to left, that distance is actually increasing between these two curves. So it makes sense that the derivative there is positive, not negative. And the reason why is because the order of subtraction needed to flip when we got in the vicinity here of x equals 2. All right, guys, and that was everything they needed in question number 4.